Welcome back to Neural Intel. Ready for another deep dive?
Always.
Awesome. Well, today we're looking at something pretty cool. Generating realistic talking portraits, from just a single image and an audio track.
Right.
And you found some cutting-edge research for us to dig into.
Yes, this paper titled Unlock Pose Diversity. Accurate and efficient implicit key point-based spatiotemporal diffusion for audio-driven talking portraits.
It's quite a mouthful.
It is, yeah. But the goal today is to really just extract those core innovations from the paper so our listeners can quickly grasp, what are the big advancements here. And we'll do it without getting too lost in the weeds, as always.
Absolutely.
And for Neural Intel, as always, we'll be focused on the what and the how from a technical perspective.
Right.
So why don't we start with, what's the core challenge here? Why is creating a realistic talking head video so difficult?
Well, on the surface, it might seem pretty straightforward.
Yeah.
But it's more than just syncing the lip movements with the audio.
Right. You need those natural variations in head pose and facial expressions. And early research, a lot of it focused so heavily on lip sync.
Yeah.
Which is, of course, it's important.
Yeah.
But neglecting the head movements, the expressions, that led to animations that, the paper puts it well, they looked stiff.
Exactly. So you could have perfect lip sync, but the person would still look like a robot almost.
Yeah.
So this paper, the researchers, they kind of break down the existing approaches to solving this into two main categories.
That's right.
Key point based and image based.
Right.
So can you walk us through those? What are the fundamental differences?
Yeah, absolutely. So let's start with key point based methods.
Okay.
The idea here is you identify specific points on the face, those key points, and then you animate those to drive the motion.
Okay.
And they often use something called the 3D morphable model, 3DMM.
3DMM, right.
And the advantage of that is it's really good at maintaining that character's identity.
Right. So you don't have that kind of weird morphing effect where it doesn't quite look like the same person?
Exactly. Yes.
Yeah.
Like you have that template.
Yeah.
But the paper talks about this fixed points limitation, right?
Right. So what is that and what kind of impact does that have on the realism of the animation?
Well, because it's using this predefined set of key points, it can miss some of the finer movements. Those nuances around the eyes or the specific way someone frowns. Those kind of details often happen between the fixed points.
I see.
So they're not really captured.
Okay.
And also making that connection between the audio and, having it naturally drive those key points has been a challenge.
Yeah, it makes sense. You're trying to get this audio to move these points in a very specific way. And there are so many subtle variations in how a face moves.
Exactly. And this leads to, they call it low pose diversity.
Okay.
So the head movements are not very varied.
Right.
They tend to be a bit repetitive. SADPOCR, they mentioned, is a key point-based method that starts with 3DMM, and therefore it inherits these limitations.
Okay. So key point, good for identity, but maybe not so good for those small, natural movements.
Right.
And maybe not as much variation in the pose. So let's move on to image-based. How do they do it?
So they kind of take a more direct approach, right?
Yeah.
Instead of working with an intermediary, like key points, they train an image generator to directly synthesize the frames of the video.
Okay.
And often these are, using diffusion networks.
Right. Powerful stuff.
Yes. And the advantage there is that they can produce, potentially very high quality portraits, a lot of detail, because they're not limited by those predefined points.
Right. So if they're generating images directly, they can get all the little wrinkles and subtle changes, right?
Exactly.
So then what's the trade-off? Because the paper mentions identity distortion and expensive computational costs.
Yeah, that's the trade-off. You get more detail.
Yeah.
But maintaining the consistent identity of the person can be a challenge.
I see.
You might see some variations from frame to frame.
Yeah.
And because it's generating these high-resolution images, it's computationally very expensive.
Yeah.
So it's slow. Not great for real-time stuff.
Right.
They give the example of VSA1, and they say that they had to make some compromises with explicit head pose control
Okay.
to make it work with that direct image generation.
So key point, good for identity, less nuanced movement.
Right.
Image-based, high quality, but slow, and maybe some identity distortion.
Exactly.
And that brings us to KDTalker, which is presented as this hybrid approach.
Yes. KDTalker, they call it a framework. And the key here is they combine unsupervised implicit 3D key point with a spatiotemporal diffusion model.
Unsupervised implicit 3D key points.
Right.
Break that down for us. What does that even mean, and how does that help with some of those limitations we've just talked about with the traditional key point methods.
Well, unlike the traditional key points, these are not predefined. They are learned from the data in an unsupervised way. And the interesting thing is that they can adapt, what they call facial information densities.
So they can change,
Yeah.
basically.
You can think of it as the model dynamically focusing on the parts of the face that are most relevant for that expression
Okay.
or that pose. And this allows them to model a wider range of poses
Yeah.
and capture those fine details that we were talking about.
That the fixed points miss.
Exactly.
Okay. And then they combine that with a spatiotemporal diffusion model.
Right.
So how does that diffusion part help, to create these realistic portraits?
So instead of predicting the key points directly, they use this diffusion process.
Hmm.
So during training, they add noise to the real facial motion data.
Okay.
And then the model learns to reverse this process.
So it starts with noise, and it has to kind of figure out how to get back to the original real motion.
Exactly. And this allows them to model the relationship between the audio and those key point movements in a more expressive way.
I see.
More nuanced, leading to, more natural-looking animations. And then they have this spatiotemporal attention mechanism that they emphasize.
Okay. What's so special about that?
Well, it's designed to achieve accurate lip synchronization. So it's not just looking at the audio at a single point.
Okay.
It's looking at the whole, over time, and also helps to produce, what they call temporally consistent animations. So that's, smooth movements across all the frames. And they say it also helps with computational efficiency compared to directly diffusing the images.
So just to recap, we have these adaptive implicit key points, the diffusion model driving that motion, and a design that aims to be efficient and preserve the original identity.
Exactly.
So can we dig a little deeper into how that sets it apart from SadTalker, for example, and some of those image-based approaches?
Yeah, for sure. So with the key points, like we said, SadTalker, they start with 3D MM, so those fixed points.
Right.
KDTalker's adaptive implicit key points, they adjust based on what's in that image.
Okay.
So much more flexible.
Yeah. Moving away from the static points seems like a big deal.
Yes. And then with the audio
Mm.
and how it drives the motion, the older methods, they relied on things like VAEs or GANs to predict the key points from audio.
Okay.
But KDTalker, using this diffusion model, they're able to capture that relationship between, what's being said and how the face moves much better.
And what about efficiency and identity preservation? How does it stack up against the image-based methods?
So those image-based methods like AnyTalker and a portrait, they use stable diffusion.
Right.
They can create detailed visuals, but they're very computationally intensive.
So slow.
Yeah. And sometimes they struggle to keep that exact identity.
Okay.
But KDTalker, by using those key points to guide the rendering, it's much more efficient.
Makes sense.
And it preserves the identity better. It also offers explicit head pose control, unlike VSA1.
Right. And I'm looking at figure 2 in the paper.
Yeah.
It shows inference time plotted against head diversity.
Right.
And the size of the circles represents, I believe, the lip sync error.
That's right, yeah. Lip sync error distance.
So what's the takeaway from that figure?
Well, you can see that KDTalker, labeled ours there, achieves good head diversity.
Mm.
But it's also pretty fast.
Okay.
And that circle is small, meaning
Right.
low error. So good lip sync. Some of the methods, they might be faster, but then the diversity suffers or the lip sync is not as accurate.
Yeah.
KDTalker seems to hit a good balance across all three.
Right. It's not sacrificing one for the other.
Exactly.
Okay. So we have a good high-level understanding now.
Right.
Let's get a little more into the weeds.
Sure.
So figure 3 shows the overall architecture.
Yeah.
Can you walk us through the main components and how they work together?
Yeah, absolutely. So they have the motion extractor,
Okay.
the audio encoder, reference-guided priors, keypoint-based spatiotemporal diffusion, and then the face render.
Okay, let's break them down one by one. So starting with motion extractor.
Okay.
It uses a pre-trained live portrait model. What does it do?
So that motion extractor, it takes that single still image that you give as input, and it pulls out the motion information from it. So the canonical key points, those represent the kind of the underlying 3D structure of the face in a neutral pose.
Okay.
It also extracts expression deformation key points. So that's how the features change to express different emotions. And then head pose parameters.
So that's the orientation and position of the head in 3D space.
Exactly. And importantly, these key points, they're flexible. They're unsupervised, so they can adapt to different faces.
Okay, so they're not fixed to the same points on every face.
Exactly. So better capture of expression and head pose. It also pulls out the appearance features.
And those are important to keep the identity consistent.
Exactly, yeah, to make sure it looks like the same person.
Okay. And then running in parallel to that, we've got the audio encoder. What's that doing?
So the audio encoder, that's using the pre-trained Wave Tulip audio encoder. And it's taking the audio track and it's processing it to extract the audio features. So basically representing the sound information in a way that the model can understand
Okay.
and use that to drive those facial movements.
So now we've got these two streams of information, the motion from the image and the sound from the audio.
Right.
How do we bring those together?
Well, that's where the reference guided priors module comes in. And you can see that in figure 4.
Okay.
It acts as a bridge.
Yeah.
It takes those canonical key points that were pulled out of the image
Okay.
and combines them with this noise sequence.
A noise sequence. What does that mean?
Well, you can think of it as adding some randomness, some variation,
Okay.
and it gives the model that initial understanding of the facial structure.
So like a starting point.
Yeah, a prior,
Yeah.
which is really important for good lip sync. And it creates a series of input tensors. They are labeled input 1 and plus 2 in figure 4. And those get fed into the diffusion model.
Okay, that's cool. It's like giving it a blueprint before it gets to work on the motion. So then we get to the core of it, the keypoint-based spatiotemporal diffusion. What's happening there?
So this is the module that uses that latent diffusion approach
Okay.
to predict the motion parameters.
Yes.
So that's the expression, deformation key points, scaling, translation, and head rotation. And the forward diffusion process is basically, it's gradually degrading a latent representation of the face and its motion
Okay.
over a bunch of time steps by adding noise. And this process, it's conditioned on those features from the image and the audio.
Right.
So during training, the model learns to predict what noise was added at each step.
And then the reverse process is where it learns to generate the motion.
Exactly. So it starts with that random noise sequence.
Okay.
And it progressively removes the noise to reconstruct the original latent representation.
Which corresponds to the motion of the face.
Exactly. And that reverse process is modeled by a neural network, which they call OITH.
Okay.
And the key part of that network is their spatiotemporal aware attention network.
All right, let's dive into that. Figure 5 shows the architecture. How does that network ensure that the motion is realistic?
It's designed to make sure that the movements are spatially coherent, meaning that different parts of the face move together naturally.
Okay.
And temporally consistent, so smooth motion over time, syncs with the audio. It uses a bunch of things. It combines the current time step of the diffusion process with the audio features.
Okay.
It uses ResNet blocks to learn the complex relationship between those audio cues and how the facial points need to adjust. But the really important part is the spatiotemporal aware self-attention.
Okay, so how does that mechanism ensure that coherence across space and time?
It uses rotary position embedding, or ROE,
Okay.
which basically gives the model a sense of where things are in both space and time. So recent movements are weighed more heavily.
So it's kind of remembering what just happened.
Yeah, exactly. And it maintains the spatial relationships between those key points.
Okay. So after the diffusion model has predicted all those motion parameters, then what? How do we actually get the video?
Right, so then it goes to the face render.
Okay.
It takes those predicted key points, which are now deformed based on those parameters from the diffusion model,
Okay.
and those appearance features from the original image, and it uses the warping and decoder from Live Portrait
Okay.
to basically deform the face and reconstruct it frame by frame. And you get the final video.
Very cool. Okay. So they did a ton of experiments
They did?
comparing KDTalker to other methods. What were the key findings there? Table 1 shows those quantitative results.
So table 1 shows that it performs really well, across a bunch of key metrics.
Okay.
On the HDTF dataset, for lip sync, it scores highest in LSEC and lowest in LSED.
Which means?
It means really accurate lip movements.
Okay.
In terms of head motion, it has the highest diversity score, so
Yeah.
natural varied head movements,
Okay.
video quality, good scores in FID and CPBD.
Okay.
So the videos look realistic and sharp.
Okay.
And the inference speed is much faster than a lot of the other methods.
Which is great for real-time application.
Yeah, over 21 frames per second. And, some aspects of its performance are almost as good as real video.
Wow, that's really impressive. And then figure 6 shows a visual comparison.
Right.
What stands out there?
So visually, you can see the lip movements are very close to the ground truth video.
Okay.
But the head movements are much more varied and rich compared to other methods like SAD Talker, Real 3D Portrait. those have very limited head motion.
Okay.
And a portrait, you can see some lip distortions there.
Hmm.
And figure 7 shows those motion heat maps. And again, you can see that KDTalker generates more diverse and natural head movements.
Very cool. And they did a user study, right?
Yes.
Where people rated the videos.
Right.
What were the findings there?
So Table 2 shows that people really preferred the videos generated by KDTalker.
Across the board.
Yeah. Lip sync, head motion, and overall naturalness. It got the highest percentage of votes in all 3.
So even though those quantitative results are great, people actually perceive the videos to be better as well.
Exactly. And, the lower naturalness scores that AnnaPortrait and Real 3D Portrait got, that kind of matches those visual issues that we saw.
Right, right. Lip distortions, lack of head movement.
Yeah. And then they did a whole bunch of ablation studies.
Right. Tables 3 through 7. Can you briefly touch upon, what were some of the key takeaways from those?
So they really highlighted the importance of different components. For example, that reference canonical keypoint and the spatiotemporal aware attention module.
So those are critical for achieving good lip sync and diversity.
Yeah, exactly. And they compared their diffusion-based approach to other generative models like VAEs and JANs,
Okay.
and showed that diffusion is better for synchronization and coherent motion. They looked at the face render module, showing the advantages of using live portrait for capturing accurate lip movements. And then they also explored the impact of the number of inference steps, finding that 50 DDIM steps is a good balance.
Okay.
And also, how many frames to use, suggesting that 64 frames gives better lip sync and head motion.
Okay, so a lot of really interesting insights there. But it's not perfect, right? They point out some limitations.
Yeah. They acknowledge that the performance is really dependent on the accuracy of that initial 3D keypoint detection.
So if the image isn't great or there's something unusual about the face, that could be a problem.
Exactly. And occlusions are a challenge.
Occlusion.
So, if parts of the face are hidden,
I see.
that can cause artifacts in the video.
Makes sense.
So, yeah, it's not perfect.
Well, I think this has been a really fascinating look at KDTalker.
Yeah.
It seems like a very clever approach to solving a very difficult problem and really pushing the boundaries of, creating these believable talking portraits.
Absolutely. It's a
Yeah.
very clever integration of different AI techniques.
And while it still has some limitations, the improvements in lip sync accuracy, head pose diversity, and the speed are pretty impressive.
Yeah, they really are.
Well, for our listeners, you can find a link to the paper in the show notes. We really encourage you to check it out. It's a fascinating read, and we'd love to hear your thoughts.
Yes.
What parts of this technology did you find most interesting from a technical standpoint? What are some of the challenges you see in its further development? Let us know. You can connect with us through the Neural Intel webpage. The link is in the bio. And as always, be sure to check back for more deep dives into the latest AI and ML research.
Thanks for listening.
Thanks for joining us.